Thank you all for coming. It's delightful to see so many old friends, even if we have trouble recognizing each other. It would be very easy to give a lecture, which basically was quotes from Alan, of which you've seen one here. This was one which was around the department for many years, and I think it summarizes some aspects of Alan, which we'll perhaps come on to later. But perhaps I'm going to, first of all, try and explain the title. The Harvest comes from this book of quotations that Alan published in the mid-1970s. And the other bit, International Tables, the crystallographers amongst you will know and love these 10 volumes, and which describe all the formalities of crystal symmetry that anybody would not want to know. And the final one, Andrew has been showing around a book of Alan's Eclectica, which I will come to later in the talk, because there's some absolutely fascinating stuff. I'm going to start with Alan's biographical notes. He came back in 1947 from working on the youth railway in Bosnia and expected to go to Cambridge to be a research student. But as you see in the second line, he says the forces of state security judged the yard with dangerous thoughts. They were right, and I still do. And he said these thoughts turned to crystallography, which you might regard as harmless, devoted to shapes of crystals, but in fact it's one which continues to revolutionize. And finally, crystallographers tend to concern themselves with real life as well, and have long form a World Wide Network. So that, I think, is a nice thread, which I hope will come through this talk. He joined the NALS lab in 1949 as a PhD student under the NAL. And like all good people, he took a Birkbeck part-time first degree. The picture, of course, is near where we're standing now. This is the old labs in Torrington Square, where I first met Bernal and first worked in the department. Bernal carefully chose, this is the opening of the lab, and on the far left there you'll see Bragg, far right you'll see Bernal. And Bernal carefully chose research teams to carry out a revolution in molecular biology and material science at X-ray diffraction, the promise. And bear in mind that X-ray diffraction was still a fairly young science at the time. And Alan joined the materials team. Now, crystallographers, close your mind, close your eyes. What I want to emphasize here is the top left. That's crystal. If you want to get hold of the structure of a molecule, which is what we actually want to do because it's the molecules that do things, then in those days you had to line them up on a lattice, throw X-rays at them, get an X-ray diffraction pattern like this, and then wave a magic wand, and you get a structure. Now, there's an awful lot involved in that magic wand, which I'm not, you will be relieved to know I'm not going to go into. But the one thing I want to emphasize here is that crystallinity was necessary for the technique to work. And so, crystallography, do with crystals. We'll come back to that, but I just want to give you a quick summary of the way I saw Alan's science developing. This is meant to be a set of histograms. The larger number of X's, the larger the number of published papers, approximately. Each cross is about 2 papers. And what I find interesting is that if you look at what we're calling classical crystallography, the stuff I've just talked about, put stuff in the crystal and take diffraction patterns off. He started in the 50s with normal crystallography, and as he developed, things moved. That sort of kind of work sort of began to fall off. He did a fair amount of technical development, theoretical and experimental, and that started at the beginning, faded and bumped a bit later on. But then the work that I think most of you who come across Alan will actually resonate with comes under the title of generalized crystallography, which we'll talk a bit about later. And I've classified this as pentagonal, to do with 5-fold symmetry, which crystallographers hate. General, which we'll talk about a bit, and then surfaces, which is where, well, you can see how this grew. and then faded again. And this is where quasicrystals were discovered. And this is a lot of the work he did with general aspects of structure and function. And then towards the end, he retired in 1991 and spent a lot of his time working on surfaces, of which you've seen many examples outside. Right, let's start with the classical crystallography, the normal work. Noticeable that this work was slanted towards real problems. It was immediately post-war. Calcium phosphates was part of his thesis. Structure of calcium phosphates is obviously relevant to bones, health. Silicates, obviously relevant to the construction industry. Corrosion of materials, ditto. He was an expert on rusting. And on solid state phase transitions, trying to understand how crystals might change their structure in the solid state. And this has some interesting applications in geology if you're trying to actually use magnetism to work out which proto-continent was where when. If you don't get the crystallography right, you might end up with your Earth in the wrong shape. He made early use of electron microscopy and electron diffraction and began to explore solutions in structures in solution, which is where I began to make contact with him because that was where my focus lay. I'm not going to show lots of scientific slides, but this is just, don't worry about looking at the detail of it, but this is from one of his papers on iron oxides hydroxide system, the Russian system. Looking at the structures of various hydroxides as a function of oxidation and dehydration, what were their structures? How did they convert from one to another? What are the ranges of composition of different phases? Just give you an example of the kind of map that he built up on a particular, really very important system. He made some early theoretical advances in the analysis of the X-ray data, how to go from that set of spots to a structure. He was very interested in the theory of symmetry, anti-symmetry, when you actually don't just move something from one place to another, but you move it to another place and invert it, or change color. And to many of us at the time, this seemed a bit obscure. In fact, there's potentially lots of experimental relevance to crystal properties. And then he also began to extend considerations of symmetry into 4 dimensions. And he was adapting with instrumentation, which I didn't know until I began to look through many of the papers that he's written. There's 3 examples here of cameras. There's 2 examples of cameras and one of the crystals. And he took out patents on 2 of these. And this thing down, this comment down here in the corner, ECG, is to remind me that his father was a GP. And his GP got hold of an early ECG sheet. Didn't work. So Alan amended it. So again, I didn't know Alan had a dub hand in this sort of thing. I think if you talk to the family, you find out you know a lot of stuff as well. So now let's move on to what I think most people remember Alan for, what I call pentagon. And you see here that the intensity of the work builds up from the 60s. His first relevant paper in this respect was in 1962. It built up to the, I should say, the chaos of quasicrystals, which I'll talk about when we come to it, and then faded off in the 90s. Now, let's come back to international tables. It's vital for crystallographers. Because of the fact that international tables make crystallographers sort of focus all the time on symmetry and things being in a lattice, he thought that this had been a factor inhibiting the growth of crystallography, because they only allow you to describe something in terms of what something is like in a crystal. And he said, in fact, the opposite is the case. The space group arises from the local interactions of the components. Only from the local interactions of the components. And he said this is unsuitable for dealing with binomial structures. But even for crystals, they're inadequate. They can't deal with defects, dislocations, variable composition. And it's the structure of the molecule itself which is primary. And as I've tried to emphasize, crystallization is simply a means to an end. If you could do away with having to put these things into crystals, molecules into crystals, then you wouldn't bother doing so. And as many of you know, that is now becoming possible. Again, he said this emphasis periodicity is somewhat distorted the development of crystallography. And he said, well, perhaps we should ask something different. Out of what range are identical points required to have identical surroundings to generate crystallinity? And this is an echo of work he quoted when he developed this of Boris Delony, a Russian in 1934, who Alan met in 1962. He wrote this book on the mathematical foundations of structure analysis of crystals, of which there's a picture here. Thank you to Marjorie Senthal, who I hope is online today. And this is a copy of that book, which Alan gave to Marjorie in, I think, 2017. And Alan felt that this approach was more suitable for a unified theory of crystals, hierarchic, amorphous, or disordered crystals. And so we come to this 1962 paper. And instead of putting atoms or spheres on a lattice, why don't we start with a central sphere and start putting other spheres around it? And there are several ways in which you can do that, some of which you can repeat in 3 dimensions. But this, the icosahedron, you can't. It's just one sphere with 12.
Bring your drink in a minute.
Thank you.
Volume too loud. Alan then took that icosahedron and he put 2 more shells of spheres around it and described the properties of that. And this came known as the Mackay icosahedron. It certainly won't repeat in a lattice, but he argued this still we should be considering as a crystal. I'm not going to go into any detail on this, but just to say that the workers in various fields say that this has had a tremendous impact on a range of fields, particles, clusters, intermetallics, and quasicrystals, which we'll come to. And with nanoscience and nanotechnology, these are very small, only tens, hundreds of atoms. And if you look at certain nano clusters, you will tend to find that they often form this sort of structure. And it's been extended to related local structures which have these lovely names: anti-Mackay, double Mackay, pseudo-Mackay, interesting adjectives which we might actually think of applying to some of Alan's ideas. Anyway, these are representative structures in real systems, of which I'm going to show some pretties. Don't worry too much about them. This is an gallium magnesium palladium alloy, and you can see there these sorts of structures are packing together to give you the structure of the intermetallic. Is the screen? Yeah. Okay. And there's another one. So lots of pretty pictures, and I think you can see kind of way in which these structures are put together. You've got some obvious icosahedral structures here, and these are building on this icosahedral framework. Now, the trouble is, for a crystallographer, is the icosahedron has 5-fold symmetry. You turn it around by 72 degrees, and it repeats itself. You do that 5 times. So what? Oh, so what is you have a nightmare, because if I want to put polygons together to form a repeating structure, I can do it with triangles, I can do it with squares, I can do it with hexagons. Where's the 5? There it is. You can't tessellate pentagons. You can't get those pentagons to fit together in a 2-dimensional structure without creating gaps, as on there. So if we can't tile the surface periodically with a pentagon, perhaps we should get away with thinking all interesting crystals are periodically repeated. Can they be non-periodically repeated to fill space? Now, this isn't a problem that Alan invented. It's a long-standing problem. And many people, many mathematicians have worked on it. And I get it in these 4 bullets. A long-standing problem. 1964, Robert Berger solved the problem, but he had to use 104 different shapes to do it, which is a bit much. This guy, Rafa Robinson, 10 years later, reduced it to 24. Alan, in the mid-70s, reduced it to 2. Can't do it in less than 2 because that would then tessellate, but he did it in 2. And notice that I've suggested, I've commented where he actually made this point publicly first, which is in lecture in 1975 in Yugoslavia, as what then was. And it was published in this journal, which I'm not going to try and pronounce, but you won't be surprised to know that not many people read it. I read it. Not many English and certainly not many Americans would ever read it. So in a way, this is something that I note about Alan. He didn't worry about where he published. He went to this meeting. He was interested in the meeting. The people were interested in what he wanted to say, and he published in their journal. But we didn't see it. If we had, Alan might have been the first to have actually done this filling of the plane with 2 different dominators. This is from that paper. You can see on the folds, on the far left there, filling of space with pentagons and with isosceles triangles. But then if you look at the pentagon, you can divide the pentagon into 4 different tiles, an A tile and a B tile, both isosceles triangles. So you can then go back to that picture there, and you can put those labels on, and you find you've filled the 2-dimensional space. The trouble is, Oliver Penrose published first, 1 year beforehand, with these so-called kites. This is very small. Kites and the darts. And you can make these beautiful pictures, and you see that they fill the surface. But Alan's tiles are components of Penrose's. We're basically talking about the same system, the same pair of dominoes. And I've tried to show here in colour the kites and the darts superimposed upon part of Alan's structure. So, Alan was there up right at the front, and more or less simultaneous to Penrose made this reduction to 2. And more or less, more than that, he was the first to ever take a diffraction pattern. And have a look at that and see if you can see what the symmetry is. It's tenfold. It shows 5-fold, it's tenfold. So a crystallographer would look at that and say, I don't believe that. That can't be a crystal. But it fills space. So why shouldn't it be a crystal? Why does a crystal have to be periodic? It only has to be periodic because that means we can do a diffraction experiment to find the structure of the molecule. Now, can this be done in 3 dimensions rather than just playing around on a piece of paper on a surface, on a flat surface? Well, the answer is yes. And Alan showed it could be in a paper which celebrated the 60th birthday of Boris Feinstein, who ran the crystallography department in Moscow State University. I said 1982, it's 1981. And if you read this paper, it's largely about the 2-dimensional case. But in the last paragraph, in the last section, there's a, oh, sorry, I should show this. He called the paper the Neve Conquegula on the pentagonal snowflake. And a nice computer drawing there that Bob Mackay did for the paper. And you'll notice it was published in a journal which we all read, Soviet Physics. Obviously, because it was a birthday celebration for Boris Feinstein. It's a nice, the reason, the pentagonal snowflake is an echo of a paper by Johannes Kepler on the 6-cornered snowflake. And I think Kepler was the first to actually suggest that the reason the snowflake is got 6-fold symmetry is because the atoms or the molecules that make it up pack together with that sort of symmetry. So the beginning of this penultimate paragraph, he just says the same kind of construction can be made in 3 dimensions. Oh yeah, right, great. Yeah. That's actually quite astounding. And he worked out what they were. He had just 2 basic polyhedra, obtuse rhombohedra, don't worry about the technicalities, with faces and angles in fraction of 63.43 degrees. And if you're into crossing your eyes to see stereo pairs, you might get some feeling for what that's like. But just out of the blue, hey, I've done it. So what? It's easy. Okay, that's fine. But can these structures be made? His paper concluded with that statement, which I think I've highlighted the bits which I think I'd like to stress. He said this is an example of a pattern which might be encountered, but if it's unexpected, it might be missed. There's quite a lot in that statement, because if you're a scientist and you're doing something and something unexpected happens, some people would just forget, oh, that's a quirk, it's wrong, it must be something, people forget about it. In fact, one of the things I used to pass on my students at UCL, if something doesn't fit, then there may well be something really interesting there if you dig down deeper. So it might go unrecognized if unexpected. And one was actually encountered a year later in the preparation of an aluminium manganese alloy, though it wasn't recognized to be this sort of structure for a further couple of years. It was unexpected, therefore unrecognized. That didn't stop the Nobel Prize Committee from giving the Nobel Prize to Dan Shechtman from the Weizmann Institute. It's a picture of Dan holding an icosahedron for obvious reasons and showing a diffraction pattern from part of this, showing again it's got this 10-fold rotational symmetry. Okay, but why did Dan get it? Well, I'm just going to show this slide because I feel quite strongly about this. Higgs boson. Peter Higgs predicted it existed in 1964. Millions and millions and millions and millions and millions of pounds were spent trying to actually find it. It was discovered in 2012 at CERN, and Higgs and Englert were awarded the Nobel Prize in 2013. Quasicrystals. Alan predicted the existence of this tiling in 1981. It was discovered in 1982. The diffraction pattern was published in 1984. Shechtman got the Nobel Prize, and Alan didn't. wasn't involved, despite the fact he was the first one who actually predicted they could exist. Shut up. Alan said he got a consolation prize, together with Steinhardt and Levine, who worked on this system as well, by giving the Oliver Buckley Prize in 2010. And there's a picture there of Oliver Penrose with Alan and Roger Penrose. And I think that's a nice statement. We hope that there could be some consolation in seeing your clear predictions having become accepted as mainstream crystallography. Well done, Alan. I don't think you really married it, but I think, no, whatever. Right. On a similar sort of theme, I'm going to come back to the Harvest of a Quiet Eye. This was published, I think, first in 1977. And then the Institute of Physics took it up and published a dictionary of scientific quotations, basically the same book. And then some years later, Oxford University Press produced a dictionary of scientific quotations without much recognition of where the original idea and most of the quotes came from. Alan accomplished a lot, and a lot was not recognized. However, he finally was elected to the Royal Society in '88. And it's so right. I was going to try and show you his signature's on there. He's sitting there. Oops. Oh, guy down there. And this is an extract from his citation. Furthering understanding of quasi-crystalline iconcecal phases, which I've talked about, predicted the occurrence of five-fold symmetry, computed the diffraction pattern as expected, a leading authority on the geometry and symmetry of crystals, elaborated the importance of the Penrose pattern for crystallography, and made noteworthy use of quaternions in crystallographic calculations. Well, we won't worry about that one. Quaternions are a bit technical. So he got at least the recognition from the Royal Society. It didn't go to his head, because this is what he said about it. It relieved the pressures in the face of demands to assess academic productivity, but brought no material difference. So it didn't go to his head, but I think he probably appreciated it. Right. Okay. I say a bit about the generalized crystallography. What is generalized crystallography? Quasicrystals is one example. It builds on concepts developed by Bernal, and he spent some time working on it. And look at just he said, crystallography really is becoming the science of structure. Being concerned with structures bigger than those represented by simple atoms. And the aim of generalized crystallography is to understand the properties of matter at a human scale in terms of the arrangement and operation of atoms. The science of structure deals with form and function, the way in which large-scale form is the expression of local force. Again, it's the way the atoms interact, not the fact that you put them on, hung them on the lattice. Again, just to give an example, don't try and read it all. He saw connections between apparently disparate areas of science. He got classical crystallography in the middle, and then all the way around, a whole range of things, which don't worry if you can't read them, but you can see there's an awful lot of things there. And he saw connections between them in the structural sense. Fibers, Fibonacci problem, maximum entropy, three-dimensional integrated circuits, pleiotropic liquid crystals, cellular autonomous computer graphics. He saw connections there within what he called generalized crystallography. And the key concept is that of hierarchy. In that in a large structure, you can distinguish smaller substructures in which the internal relations are stronger than the external ones in binding them together. And the example he used was atoms, amino acids, alpha helix, fibril muscle. And Bernal would say molecules, polymers, polymers of polymers. And these structures evince new properties with increasing size. And the properties are often at the level of the aggregate. We want to understand how new properties emerge from the combination of simple units. And he made a number of contributions here. He was an ambassador for the idea, developed further Bernal's ideas, and developed alternative descriptors instead of just going the international tables route. And then moved into non-planar two-dimensional surfaces for the last few years of his activity. And you see, what are they? Well, you envisage atoms as being embedded in curved sheets rather than in flat layers, as in crystallography. And these are called periodic minimal surfaces, which can help with the visualization structure at a level above that of single atoms, and has wider structural uses. Soap films is an example. Application of structural science, this is the unit cell of cesium chloride. The surface over there shows the zero equipotential surface of cesium chloride. This is something which is close to my heart. This is I7, which consists of two disconnected networks of water molecules, and that surface separates the two non-connected. There are more applications in biological structures, lyotrophic colloids, zeolites, and also in structural engineering. And more, and you can see more outside. Now, as those of you knew Alan know, he was interested much broader than just the science. And this is where we bring back eclectic. He was once introduced to somebody as the well-known eclectic. And because of that, I think he said, okay, I'm going to put stuff together, and that's what I'm going to call it. And he produced this in 2009, and it's got some fascinating stuff. Some of the non-crystallographic writings, don't bother reading them all, just look at a couple of these, and you'll see there's a heck of a range of stuff there that he is working on and publishing on. It's not right sending this off to a journal and they're saying, oh, this is rubbish. You know, he's actually getting this published. Example, this is the type found of the Phaistos disc, which is from Crete, 2nd century BC, or AD, I don't remember which. And he looked at this and he tried to work out how it was actually inscribed and decided, and it's about a 10-page paper, that a set of, you know, it was, they inscribed, well, you can read it there, inscribed the clay with a stylus, baked the clay, cast in pieces of type in bronze, and then used those for making the symbols. This is a lovely title for a paper, Symmetric Celtic Sycophancy. This is a detail from a stone in the Meagle Sculptured Stone Museum in Scotland. And I won't make any comments, but apart from his comment, the characteristic Pictish talent for symmetrical designs is combined with sharp social comment. Non-crystallographic journals. Hongqi Zhoubanshe, Beijing, the Journal of Royal Central Asian Society, Science and Public Policy, Architectural Design, Perception and Psychophysics. He was a specialist on science in Asia, which I tried to cover there in yellow. And then a whole series, there are a dozen papers on science in Russia and in Asia, in India, Japan, South Korea. Deeply concerned about science and society. And these 5 bullets are my attempt to try and classify his interests. What's science? How does it work? What's the science of society? Science in society? How do you apply science to guide the operation of society? And what's the position of the scientist in society? Some of the papers there, again, you don't need to read them all. But his deep concern with science and politics flows from many of these papers. And he had his own science-based recipe for a successful future and put forward ideas on how to get over the ways that are stopping us getting there. Now, I'm just not going to go through all this list. I'm just going to talk about how does science work in terms of the way Alan worked. Well, there's the Birkbeck Lab again. How did the Birkbeck Lab make this possible? You've seen the kind of work that Alan was doing, how varied it was, how acceptable it was to the outside world, And he did this in the laboratory of crystallography, or previous to the Department of Physics. He chose problems that interested him, irrespective of the need to get funds to do it. He worked either alone or with people he resonated with. There was never, to my knowledge, a Mackay group. There was Alan and one person or another visitor. He found these collaborators worldwide. He spoke, read, and wrote in many languages, listed there, coloured the relevant countries where these are primary languages. 1, 2, 3, 4, 5, 6, 7. He spent some time and some money in the early days translating Russian papers. Papers published in even more languages. He was particularly amused to find one was republished in Georgian. And he traveled widely. This quote from Daniel, I think, summarizes his joy at traveling the world to do science and talk to scientists. The blue shadings are countries in which he actually spent time as a visiting professor, visiting researcher, where he did quite a lot of his work. But this traveling worked both ways, as Alan's sons, present here today, will know. The visiting scientists well committed with Sheila and Alan, and many scientists passed through and stayed with them. And I think it was Andrew or Caribbean Robert who said, well, if I was out late one night and came back, I didn't know who might be coming out of the bathroom in the morning. You've got a list here: Japan, India, South Korea, Turkey, Tasmania. There are six or seven on there, 140 pages, 7 times 114 is about 800 visitors passed through Manchester Road. Boris Weinstein, I mentioned before, his signature there is the first one on the line there. Nikolai Bielov, who Russian Academy of Sciences, and he's down there, 1, 2, third from the bottom, Moscow University. And Sheila's address index had several hundred cards in it, not surprisingly. What I like here, if you look at the bottom right of that, this is the only place we know that joins science to goodness and friendship. 2 up, thanks a lot, made me feel at home. I think any of us who actually interacted with Alan and Sheila will echo those words. How could this be done in the crystallography department? Was there something special about it? Bernal was asked if he organized the lab on communistic lines. And he said, no, we have only just got as far as the state of feudalism, which meant that you till the master's land 50% of the time and do your own thing for the other 50%. And as Alan said, this worked very well, as you can see from the kind of work that Alan has actually produced. Alan was very, very fond of talking over a meal or a drink. Eating together is one of the basic social institutions of science. And it's a rather interesting way of putting this. If eating is mixed with talking, then nobody can talk all the time. The picture here is the only one I could find of the old senior common room outside with David Moss, who is around, and Christine. A lot of ideas come out of eating together, of which one is the beginning of crystallography. This is a picture of the Café Lutz in Munich, where Ewald, Sommerfeld, and von Laue first came across the idea of sending X-rays into a crystal. It was all invented over probably a drink or a strong coffee. Dialogue with colleagues is important, and everybody should be interested in everything. And Bernard Crick, Eric Hobsbawm, Barbara Hardy, you could see him talking to them in the senior common room, not necessarily about physics or crystallography, but about all sorts of things which concern Alan. This is again very important to Alan as a person. Visiting researchers came through the lab. It's quite useful being near the British Museum. Two here, Linus Pauling and Buckminster Fuller. And social and political consciousness. As many of you know, Picasso came through and drew on the wall. And this used to be outside here, but it's now over in the welcome. And Paul Robeson sang in the computer room. Those of you who are doing research or have done research, you can think about how this carries on today or doesn't carry on today. I put a big question mark because I think a lot of this doesn't, a lot of the elements that were important to be able to make these developments do not exist universally in today's research institutions. But things move on. This is a quote from Alan. The old lab is long ago demolished, but I could still find my way around it in the dark. Now, I've come to the end. Do to sum up, but we've actually moved away now from assisting on the lattice. As I hinted earlier on, electron microscopy, X-ray free electron lasers, atomic force microscopy enables us to do things that we couldn't do 20, 30 years ago. And crystallography really is the science of structure, as Alan argued that it should be. What shall I remember? Well, a whole host of things, but I'll try and summarize it this way. He was a citizen of the Republic of Science, and some of his advances were not properly recognized. He was a citizen of the world, concerned that science should be making it a better place. He was a personal friend who helped me in many ways. I only wrote 2 papers with him, and so with some regret, I actually say that after one of those papers, I think to be published at some time, I think he said he'd hoped that I would actually carry on the work with him, and perhaps it was a missed opportunity. And those of you who knew, he had a great and very mischievous sense of humor. One word, some say polymath. Alan preferred to call Bernal polytropic. Of many strategies, versatile, wandering, ingenious. And I think that's a perfect description of Alan. But he's going to have the last word. There's a picture of him in one of his surfaces. Essentially acknowledging immediate colleagues, congenial Birkbeck, influences of Lucretius, Diderot, Bernal, interesting trio. Modern crystallography has taken place within the Republic of Science, a community of those who seek to acquire reliable knowledge about the natural world by verifiable experimentation rather than by revelation. And it's been a great privilege to have taken a small part of it. And from my point of view, it's been a great privilege to have known Alan and to have interacted with him and shared some interesting occasions with him. So, thank you very much.